Welcome back to another video. Today I'm going to be looking at solving linear quadratic systems. Now, if you remember in grade 10 math, you were probably learning how to solve linear systems. So you would have two linear equations, and you're trying to figure out where those two lines intersect. And you could choose between using the method of substitution or elimination. It's very similar for a linear quadratic system. We have two equations and we want to figure out where they intersect each other. The only difference is the way we solve for their points of intersection, because now we're dealing with a quadratic. So if we set a linear equation equal to a quadratic equation, that's how we can solve for their points of intersection. And once we do that, if we then treat our new equation as a solvable quadratic, we can solve for the x values that will make it true. And I will use this first example to elaborate on that. So here I have a linear equation and a quadratic. So if I set them equal to each other, and actually this should be a minus, so let me fix that there. Okay. If I set them equal to each other, what I need to do now is I need to find the x values that make this true, right? Because the only x values that will make this equation true are the x values related to the points of intersection. So the way we're going to do that is we're going to treat this as a new quadratic to solve. So I'm going to move these terms to my right side and set this to 0. And that'll look like this. And our new quadratic to solve is x squared minus 7x plus 6. Now, at this step, we could use our trusty quadratic formula, right? Because we do have an a term, a b term, and a c term to plug in. So if you wanted to, you could just use this equation to solve for the necessary x values. But I'm pretty sure we can factor this quadratic or this trinomial. So let's give that a shot. I'm looking for two values that when multiplied give me a 6, and when added give me a -7. The only numbers that are going to work are -6 and -1, meaning that my factored form of this quadratic looks like this. And then if I want to solve for my x values, I just need to set each of these brackets to 0. So if I do x minus 6 equals 0, I get one value of x equals 6. And if I do x minus 1 equals 0, I get x equals 1. Now, that's the x value of our points of intersection, but we need the full point. And the way we're going to do that is we're going to plug in our x values into one of our equations. So I'm going to pick the linear equation because it's going to be a lot faster. Let's do 6 first. That will give me a 12 minus 4, and I get a y value of 8. So my first point is a 6, 8. My second point is when x equals 1. That should be 2 minus 4. That will be -2. Therefore, my second point of intersection is 1, -2. So that's how we solve for our points of intersection. Now in this scenario, we have 2 points of intersection, right? And what's happening is our first possible scenario, where we have our quadratic and we have a linear equation that cuts right through it at two different points. So that's the scenario we just saw. There could also be a scenario where our linear equation, or our straight line, just kind of grazes past our quadratic at one specific point. Or we could also have a situation where our line does not hit our quadratic at any point, so we would have no intersection. So those are the three possible scenarios in a linear quadratic system. But how would we be able to figure out what scenario we're looking at without doing all of the busy work and solving for the question? What we can do is we can use the discriminant. And what do I mean by that? Well, if I write out the quadratic formula, this part of the quadratic formula right here is actually called the discriminant. So that's just b squared minus 4ac. And we have three rules that we can use when we look at the discriminant to figure out what scenario we're dealing with. If our discriminant is greater than 0, we have scenario number 1, where we have 2 points of intersection. If it equals 0, we only have 1 point of intersection, and that is scenario number 2. And finally, if the discriminant is less than 0, or in other words, a negative number, we would have no intersection, which is scenario number 3. So why does all this work? Well, it has to do with the fact that in the quadratic formula, we are square rooting the discriminant, right? So if b squared minus 4ac is greater than 0, that means I have a positive number to square root, and I could take either the positive value or negative value of that and get 2 possible x values when I go through with my quadratic formula. If b squared minus 4ac equals 0, and I take the square root of 0, I'm only going to get a value of, you guessed it, 0. So it doesn't really matter if I do a plus or a minus, because it's going to be the same number. And finally, if b squared minus 4ac is a negative number, you cannot square root a negative number. Therefore, you cannot find any real answer to your question, and there is, again, no intersection. So that's why the discriminant is so useful in these kinds of questions. So let's put it to use. This question asks, how many points of intersection does the following linear quadratic system have? Okay, first things first, I need to create my combined quadratic by setting these two equations equal to each other. And that will be very similar to what we did in the first question. And I'll just move all this over to the right side again. Now I need to collect my like terms. And actually, the 5 was negative on the left side, so now it should turn into a positive. So I've got to make sure I have that. And now let's collect our terms. Okay, I have a nice looking quadratic. I've got my a, my b, and my c value. Let's take a look at what our discriminant is going to look like. So B is a 4, A is a -2, and C is a 13. And as you can see, it's pretty clear that our discriminant is a positive value. Therefore, we have 2 points of intersection. Okay, let's see if we can combine everything we've gone over into a tougher question, but I'm sure you'll be able to do it. So we want to determine the point of tangency to a quadratic equation, and the tangent has a slope of -4. Before we go any further, let's figure out what this tangency means. So if I have a quadratic and I have a line that's tangential to a point, let's pick a random point here. That means that that line, or that tangent, represents the instantaneous slope at a single point. And this is a concept that you'll dive into more in grade 12 math. But for the purpose of this question, we just have to understand that if we're dealing with a tangent, we're dealing with one point of intersection on a quadratic equation. We're also given the slope of this line, but not our y-intercept. So we have kind of an incomplete equation here. And we're given a quadratic in vertex form. But I don't really like it in vertex form because I'm going to want it in standard form to collect all of my like terms. So first things first, I'm going to expand this out and put it into standard form. X plus 3 to the power of 2 will give me this. And now I just need to expand my brackets. Okay. But now we're stuck in a tricky situation because at this point I would want to set my equations equal to each other to solve for the point of tangency. However, I'm missing a value, right? I can't solve for x and my y-intercept at the same time. And just to make this a little bit easier to follow along, I'm going to change the variable name from a b to a k, right? Because in the quadratic formula, b refers to one of these terms over here. So I'll just change that to a k. So how on earth are we going to solve for this value? Well, we can think back on using the discriminant. Because we know that there's only one point of intersection, therefore, the discriminant of our new quadratic has to equal 0. So if I plug in values here, I should be able to isolate for a variable. Let's try that out. I'm going to, once again, create my new quadratic on the right side. Okay. What I can do here is when I set my A, B, and C value, I can set this entire chunk here as my C value. And then plug what I have into my discriminant. So negative 8 squared minus 4, negative 2, negative 23 minus k equals 0. So I know that was a bit of a jump, but hopefully you're following with me. What I've done is I've set these two terms in my quadratic as the variable c, plugged it in to my discriminant because I know it's equal to 0, and now I only have one variable to solve for, so that's what I'm going to do. So if I just figure everything out here, I'm running out of space. Let's see if I can just sneak some more info here. So let's continue. And this will give me negative 120 minus 8k equals 0. And I'll leave my k on the left side. So this turns into a positive 120 since I moved it to the right. And then to isolate for k, divide by negative 8, and I get a value of negative 15. And if I bring this value to my quadratic and I plug it in, I have a complete quadratic to solve that will give me the x value of my point of intersection. So negative 23 minus negative 15, these two negatives are going to cancel out. This will give me a negative 8. And now we have a perfectly solvable quadratic. So I'm going to leave the solving of the point of intersection with you guys. I hope that through watching this video you feel comfortable enough to do that on your own. If it's helpful, I can rewrite the complete linear equation because now we know the value of k, which is technically the y-intercept of our linear equation. So that was a negative 15. And now that we have a complete linear equation and a complete quadratic equation, that's why I was able to create our combined equation down here, which is solvable. And here's a little hint. This should be your answer. But again, it would be really good to try it on your own just to understand the steps needed to get to that point. Thank you so much for watching. Hopefully you found this helpful, and good luck studying.